Okay, so I thought I'd start off by representing the last thing we did on Friday, just because I feel like maybe that wasn't clear enough. Remember when we were showing that if you have something like this, then where alpha is some real number, right? And p is some positive number, then this is going to go to 0, right? As n goes to infinity, right? So right, and so the idea was to use the binomial theorem, right? So I'm just representing what we did on. Those of you who came in late, I'm representing what we did at the very end. The idea is to use the binomial theorem, right? So you say, okay, well, 1 plus p to the n is going to be greater than n choose k, p to the k, right? For any n and any k, right? Because when we take this to the for any n k where k is small, less than or equal to n. Right, and recall that n choose k is n factorial over k factorial times n minus k factorial. Right, so we get this sort of thing. Okay. So we get this. This thing is bigger than or equal to this thing, so 1 over it, right? So of course, 1 over 1 plus p to the n is smaller than 1 over that, right? So we get right, we get n factorial on the bottom, p to the k factorial, n minus k factorial, right? So, and then multiply both sides by n to the alpha. Right. Okay. So so now what we do is we notice that this n choose k factorial over n factorial, well, that's 1 over n times n minus 1, n minus 2, dot, n minus k plus 1. Right? So that's okay? Yep. Right. Okay. So we rewrite this thing here as n to the alpha over n minus 1, n minus 2, dot, n minus k minus 1, right? That's these things. And then we have this other term, k factorial over p to the k, right? That thing that thing doesn't depend on n at all. Okay, right? And we're trying to show that we can make this thing go to 0, right? We're trying to make this thing go to 0. So the way you want to think about it, I'm going to erase this thing. The way you want to think about it is that suppose that k is tiny. Suppose k is really tiny. Okay, we'll make that clear in a second, right? If k is tiny, well, then what's this thing going to be here? Then you're subtracting off terms. At most you're subtracting off k here, but k is tiny. Okay, we're going to make k tiny, and so these are all basically n, right? So this is the idea, right? If k is tiny, then the denominator, this thing, is basically n to the k, right? Because we're subtracting off something that doesn't really matter that much. Okay, right? So we get n to the k, and then so what we would get on the left would be n to the alpha minus k, right? So you just have to choose an alpha. You just have to choose a k. So So make sure that k is bigger than alpha, right? Make sure that k is bigger than alpha, then this thing is going to be have a negative power on it. So this thing would be basically n to a negative power times something that depends on k, and then as n goes to infinity, it goes to 0, right? So that's basically the idea, right? So there's two things that you need to do. One, you need to make sure k is tiny. So what does tiny mean? So what does tiny mean? Right? It means that it shouldn't that it should be small relative to n, right? So that for example, let's say that k is let's say that n is bigger than 10k. Okay, so k is so small, or n is so big then it's bigger than 10k, right? Then let me make sure. Right. Then of course k over n is smaller than 1/10. Right? K over n is smaller than 1/10. In other words, k is smaller than 1/10 of n. Right? K is smaller than 1/10 of n. So when you subtract, n minus k is going to be bigger than 9/10 of n. Right? You're going to lose at most a tenth of n. Right? So, right now each of these terms here is bigger than n minus k. Right? We're subtracting n minus 1, subtracting down to n minus k minus 1. It's still bigger than n minus k. Yes? Right? So each of these terms here is bigger than 9/10 of n. Right? So what we get here is that it's bigger than 9/10 of n quantity to the k. Right? But that's still okay, right? It's just a constant times some power of k. Right? Right? Is that right? Let me make sure I'm not saying something crazy here.
Like the whole idea is to make n to be in the denominator because we are comparing.
Yeah. We're good. Yeah, we're good. Right. So right. So what do we get? We get that this thing, right? This thing is going to be this thing is going to be smaller than 1 over that, right? So 1 over 9/10 k n to the k and alpha k factorial pk. And let me move this term over here. 9/10 pk, right? And so so then as long as we choose k bigger than alpha, so when you're writing out the proof, you'd say, well, choose k bigger than alpha, right? And then for n that are n bigger than 10k, for n bigger than 10k, we have this relation, right? Then for n bigger than 10k, this thing is smaller than n to the alpha minus k times this constant, 9/10 to the k, p to the k. Right? And this is a negative power, so as n goes to infinity, it goes to 0. Okay. But this is, I think there's two ideas involved in this proof. one is use the binomial theorem, right? Use the binomial theorem. And then second is, think about think about what this would look like. If we are allowed to, n is going to go to infinity anyway, right? N is going to go to infinity anyway. So when once n gets big enough, once n gets big enough, then these guys are all basically n, right? These guys are all basically n, and so this is basically n to the alpha minus k. Right, that's the point. Yeah, Wong.
So we have seen three proofs involving using the binomial theorem.
Yeah.
However, I see that two of them use one single term, while the other use a combination of terms. So I was just wondering, I think I get the idea of using binomial theorem to make the comparison, and making sure that n satisfy our need.
Yeah.
But that choice of combination versus single term is pretty ambiguous to me. It feels like you need experiment.
Yeah, you need to experiment. I think that's the right attitude. You don't know from the beginning, right? But if you mess around a little, then maybe it becomes clear what you need to use. Yeah. Okay. So I hope that's clearer than it was. Okay. So we just finished a bunch of examples of doing actual limits with your hands. So we've just finished some examples of basically getting your hands dirty with analysis, right? And now we're going to sort of back off into the general world of what people call general abstract nonsense. Okay. Okay. So subsequences. Subsequences. Okay, so Ellie, you haven't missed much. I just went over the last thing we did in class on Friday, so you missed basically nothing. Okay, so right. So what's a subsequence? You have a sequence, and then if you have an increasing, sequence, so maybe I should make it clear, it's strictly increasing in n, then we call P sub n sub k, as k goes from 1 to infinity, a subsequence of the original sequence. Okay, so this, I don't know if this definition is opaque at all, but let me try to make it clearer if it is. Okay, so you have some sequence, right? And then what you have here is a choice of indices, right? This is just a selection of indices that has to be strictly increasing. So, right? So you what's a subsequence? In the normal way of thinking, it's just some sequence that takes some of the numbers, right? It's just a sequence that selects some it's a subsequence of the original sequence, right? That's what this sequence of indices gives you, right? This is really a sequence of indices, right? It's just all it's talking about is this n sub k is referring to these selected indices on the way up, right? This sequence here, 1, 3, 6, 8, 10, et cetera, specifies a subsequence of the original sequence. Okay. So this is n1, this is n2, this is n3, this is n4, this is n4, et cetera, right? And the sequence is, p sub n sub 1, p sub n sub 2, p sub n sub 3, p sub n sub 4, et cetera, et cetera. Okay. Is that clear what this means? Yeah, sure.
Why does it have to be strictly increasing?
Well, if it were just increasing, then it could get stuck on one number, and then it would repeat this thing, and maybe the number isn't repeated in the original sequence, right? So like, if my sequence were n1 equals 1, n2 equals 1, n3 equals 1, and 4 equals 1, et cetera, right? Then my sequence would be P1, 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 which is not a subsequence of this is, right? Like if this is 1, 2, 3, 4, 5, 6, blah, 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 then 1, 1, 1, 1, 1, 1, 1 isn't, you don't consider that to be a subsequence, right? It has to be, you have to move along the line as the time increases.
But it could be strictly decreasing too.
No, because because then you're running backwards down your sequence, right? Then your indices will be going backwards, right? Like if I have a sequence 1, 2, 3, 4, 5, 6, blah blah blah, I don't consider 3, 2, 1 a subsequence of this. Okay, I don't consider 3, 2, 1 to be a subsequence. It has to, like 1, 3, 5, 7, blah blah blah. That's considered a subsequence, but not. It has to be progressing in the same order as the original sequence. Yeah, for a sequence, the order really matters. Okay. So remark: a sequence converges if and only if every subsequence converges. Maybe I'm just leave off this. It doesn't mean anything. Every subsequence converges. Okay. A sequence converges if and only if every subsequence converges. One direction is trivial. If every subsequence converges, well, you could take the strictly increasing sequence that is just the original sequence, right? You could take the indices that correspond to the original indices. That still counts as a subsequence. The sequence counts as a subsequence of itself, right? Because, right, you can just take nk and let that be equal to k, right? That's a strictly increasing in n, and that would just specify our original sequence, right? So let n sub k is equal to k. P n k is just p sub k, the original sequence. Okay. Going forwards, right? If P sub n converges, then every subsequence converges. Okay. Why does that seem reasonable? Does anybody have a feeling about that? Does that seem like, so, right, think convergence means, right, you've got your sequence. Convergence means that, there's some L that these guys get closer to, right? It means, more precisely that given any tolerance, there's a time past which everybody lies in the tolerance, right? There's a time past which all these guys satisfy that tolerance. Okay, well, if I've got a subsequence, that's still going to be, right? That's still going to eventually exceed this point here, right? And then past that point, everybody in my subsequence will satisfy the tolerance, right? So that's basically the proof. You say, well, look, you want to show that given, let's say that P sub n converges to some number L. We want to show that any subsequence P sub n sub k, where n sub k is increasing, strictly increasing, also converges to L. Right? Well, given any epsilon, we know that since P sub n converges to L, we know that there exists a time past which the distance between P sub n and L is smaller than epsilon. Right? But then since n sub k is increasing, there exists a k past which all n sub k are bigger than n. Right? So, and thus, the distance between P sub n sub k and L is smaller than epsilon, right, for all k bigger than k. Right? And that's what we wanted. Right? We wanted to find a time past which all the subsequence guys were close to L. Okay, does that make sense? Right, I think, in some sense, the idea is simple. It's just a matter of knowing how to write it down, right? Say, okay, what do we want to show? We want to show that there's a time, there's an index, there's a time past which, everybody is within epsilon of L. We know that there's an index for the original sequence, right? This is the index, this is the time for the original sequence past which everybody is smaller than epsilon. We know that there's a time, there's an index, since these guys are increasing, et cetera, et cetera. Okay. Let me have you try the next one. Okay, so here's the theorem. P sub n a sequence in X a metric space. Okay. Then if X is compact, then some subsequence of P sub n converges to X. Okay, so I'll let you think about it for a minute and see if you can come up with some ideas. You don't have to prove the whole thing, but just think of some things that might be relevant. chat to somebody nearby and just talk with them about anything related to this?
I'm just thinking between the subsequent when I subsequence, but I forgot to decide can prove the sequence converges in the compact
What if,
space.
so Pn.
Yes, I'm not. All I did was
In the Pn, so we can
finite
take
subcover.
the finite number, like, if we cover it with a finite number. It doesn't, it's about, right.
So maybe I should say that it will be helpful to divide it into two cases where if you look at the so let E denote the range, the image of P sub n. It would be useful to divide into two cases. Case one, where I remember why I stopped using this. Case one, where E is finite, and case two, where E is infinite. So like, if your sequence is all the same point, right? Suppose your sequence is just like P1 is some point, and P2 is that same point, and P3 is that same point, blah, blah, blah. Then the image is finite, right? Or maybe there's just a couple of different points, right? Right, so like, right, so here's your metric space X, that means P, right? Maybe P1 is here, and P2 is here, and P3 is here. But then after that, there's no new points, right? Maybe your image is finite, right? So we'll divide it into two cases. If E is finite, and if E is actually infinite. Let me get this one out of the way first. So if E is finite, then what do you see that you're guaranteed a convergent sequence, right? Because if E is finite, then one of the points gets hit infinitely many times, right? By the pigeonhole principle, right? If you've got infinitely many pigeons and finite many holes, well, one of the holes must have infinitely many pigeons in it. They can't all have finitely many pigeons, right? Okay, so then just choose that one, and then choose all the indices that get mapped to that one, and that will be your convergent sequence, right? So maybe I won't write that out. I'll let you try to write that out. Okay, so like right, it starts off proof. If E is finite, then there exists a point P and X such that P sub n equals P for infinitely many n. Right. And that's basically the end. Right. For infinitely many, for infinitely many n. So just put those guys in order and call that your new sequence. Okay. So the more interesting one is E infinite. E infinite. So now we've got x, x is compact, remember. So x is compact, and you've got infinitely many images. Right. Okay. Infinitely many images here. So, any reminiscent of anything? Any bells going off? Anybody? Other than that? And other than and? In addition to and? And.
Well, could we like turn it into a finite problem because we could cover the infinite number of points of a finite subcode?
Oh. Let's see. So you're saying cover each of those guys. Yes, you can. Let me try to get you to say something. You've got a compact set, and you've got infinitely many points inside this compact set. Do you remember any theorem about this? Like any theorem? Compact set, infinitely many points inside the compact set. You're guaranteed something happens. Anybody remember? I'll give 5 seconds. 4, 3, 2, 1. You're guaranteed a limit point. Remember? Compact set, infinitely many points, you're guaranteed a limit point. So yes, and we could go the way that you're going, but we'll end up proving this theorem. Yeah. So proof 1. E is infinite. E is an infinite set inside a compact set. A compact set. So you're guaranteed there exists some P that is a limit point of E. Okay, so you know what a limit point is, right? There's this guy here, and you know, it might be, yeah. Well, you got your what's a limit point? You all remember, I hope, right? That every punctured neighborhood contains a an element of E, right? So whatever, if we take like, I think probably the thing to do is to take radii of 1 over n, as we often do, and then say, okay, we know that there's somebody in there, E sub n, right? Okay, so let's just sort of construct it. Let the radius, right, so. Consider epsilon equals 1. Let me write it over here. Right. Consider the radius epsilon equals 1. We know there exists some E in E such that the distance between P and E is smaller than 1. Okay, so, right, and E is of course the set of all, the set of all images, P1, P2, blah, 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 blah. Right, so, we know that E equals P sub n for some n. Call that n sub 1. Right. Call n sub 1. Okay, so we've got our first element in our sequence. Okay, what are we going to do next? Consider epsilon to be 1/2. Right, we know that there's, now it gets a little bit tricky. Slightly tricky. We know that we could say, we know there's some E in there where the distance is smaller than 1/2, we know that E is equal to P sub n for some n. We call that n sub 2. Would that work? Does anybody see why this doesn't work? There's a problem here.
It might duplicate the previous one.
They might be in the wrong order.
Yeah,
They might
yeah,
be in the
yeah,
wrong
yeah.
order. Yeah, so this P sub n, the P sub n you choose, that n might be smaller than n sub 1,
Yeah.
right? But you know actually that there are infinitely many guys inside there, right? That was, right? It's a limit point, so you actually know that there's infinitely many guys inside there. So, take epsilon to be n over 2. We know actually that there are we know that we can choose an n2 bigger than n1 such that Pn2 lies inside, the distance from Pn2 to P is smaller than 1/2, right? And then so on and so forth, right? And we can do that because we know there's infinitely many guys inside there. Okay, and then we just continue in this way. So what we've just shown is that if you have a sequence, if you have a sequence inside of a compact set, then it has a convergent subsequence. Right? So as a consequence, as a corollary, every bounded sequence in Rk has a convergent subsequence. Is that clear? Can anybody tell me why that's clear? We just showed that if you have a compact space and a sequence inside of it, you're guaranteed a convergent subsequence. Now I'm saying if you're a bounded sequence in Rk, you're guaranteed a convergent subsequence. Why is that true? Yeah, sure.
Is it like Heine-Borel that if it's bounded, then it's compact?
It's you're close. If it's bounded and closed, then it's compact.
Right.
Yeah. So this guy sits inside. This is a bounded sequence. That means it sits inside of some ball, right? Right. It's a sequence sitting inside of some ball, right? So what you do is you just close the ball, right? Just take the closure of the ball. That's compact. Then you're sitting inside of a compact set. Yeah. So yeah, basically you use Heine-Borel. You say, look, this thing sits inside of some K cell. K cells are compact. Okay. Right, proof. The sequence lies inside a K cell, which is compact. Okay. Everybody okay? Everybody all right? Okay, so now we get to the big idea. We get back to the big idea, kind of back to the big original question, which was, what does R have that Q does not have? Right? And what was our original answer? We gave an answer to this earlier. What was so good about R? What did R have that Q did not have? What made R so special?
A few thing.
What?
I think it's a field.
It's a field, but Q is also a field. Right?
Oh,
They're
okay.
both fields. Anybody remember? And?
Well, it's complete analytically, or it has the irrational numbers.
Did anybody remember the term that I'm thinking of?
Density?
No. Close.
The Archimedean property?
No. That's a consequence. Both of those are consequences of.
Good.
Does it have to do with like the root 2 sort of thing?
It's related.
The limit points?
You're getting closer or farther. I don't know. Anybody? The 2, 1 least upper bound property. Least upper bound, right? Right. What does R have that the Q doesn't have? Least upper bound property. That's how you make R, right? That's how you make R. R is constructed to be the thing that contains Q as a subfield and has the least upper bound property. I guess we didn't actually prove that, but anyway, that was what we said R had that Q didn't have. Okay, so that was one way of thinking about it. Now we're going to present another sort of a different but actually equivalent viewpoint of giving an answer to this question, which is has to do with this idea of Cauchy sequences. So we'll provide an alternate but actually equivalent answer. From the sequence viewpoint. Okay, and that will be, as Anne mentioned, this idea of something called completeness. Okay. But to define completeness, we need to go a little bit, we need to lay some groundwork first. So we need to introduce the notion of a Cauchy sequence. Okay. So, so as usual, we've got some sequence. We have a metric space. So we've got a sequence and we've got a metric space. And we say the sequence is Cauchy if it satisfies a particular property, and that is given any epsilon greater than 0, there exists a time such that if you take any 2 points past that time, then the distance between those 2 points is smaller than epsilon. Okay, so this is a little bit different from convergence, right? When you're talking about convergence, rather you have a limit point, right? A point that acts as your limit, and you say there's a time past which any one point will be close to that limit. This is rather saying, given any distance, there's a time past which everybody is close to each other, right? Everybody is within that distance of each other. Okay. Shelley, what are you thinking?
Oh, I don't know. This was just sort of reminding me a bit of uniform continuity, and I know it's very different, but I'm just thinking of like the distance between two, and I guess I'm just trying to think of the consequences of I'm sure.
Okay. Okay. Yeah, I guess the phrasing is kind of similar. The phrasing is kind of similar. Okay. So let me, let's see. Okay, so okay, let me so here is sort of an alternate view of Cauchy sequences, or Cauchiness, which is actually something that people say. Okay, so to do that, we need the notion of a diameter. So let E be a subset of X, the metric space. Okay. And then let S be the set of all distances. Okay, so take distances between P and Q, where P and Q are in E. Okay, so it's a set of all possible distances, right? So like you've got a bunch of points and you measure all the distances, right? Whatever. Yeah. You measure all the distances. Okay. Call that set of numbers S. Okay. We define the diameter of P as the supremum of that set of numbers. Because that, you could have some infinite set here, and maybe it doesn't reach a max. But you can always take the supremum. Well, yeah, could be infinite. Okay, so let me introduce a tiny bit of notation. If you have a sequence, we denote let E sub n be defined as P sub n plus 1, P sub n plus 2, etc. So it's what we call the tail of the sequence. Right? Starting at a particular point, everything past that point. Okay, so then here's the point. A sequence is Cauchy if and only if the size of the diameter of the tails goes to 0. The sequence is Cauchy if and only if the diameter of the tails goes to 0. Right? That is basically just a direct translation of Cauchiness into this language. Okay. So it's almost a tautology, right? What does Cauchy mean? Right? Cauchy means that if you have an epsilon, you can find a time past which all points are, the distance between any points is smaller than epsilon, right? What this is saying, that's the same thing as saying that the diameter of the tail is smaller than epsilon, right? That's exactly the same thing, right? The diameter, like all points past this point in time are within epsilon of each other, right? Yeah. I guess it's a little bit off, but it's almost exactly the same thing. Okay. So yeah, I'll let you. I'm not going to prove that one, so I'll let you think about it. It's basically the same thing, right? If the tail's diameter goes to 0, that means that you can make all the points. You can get points within epsilon of each other, right? That's exactly what That's what Cauchiness is. Right. Okay, so okay, we'll start from there. Not next time, but the time after. Next time we have a test.
Okay.
Yeah. Yeah. Turn in the homework on Friday. Do not you don't have to turn in the homework next class. There's some small homework, I think, right? But it's due on Friday. What?
I think Friday's a holiday.
Friday's a holiday. What? What? Say the Shabbos day? I always. Okay, turn it in on a Monday.
Thank you.
Okay, see y'all.
Looking over.
Bye-bye. See you. Are you coming office hours, Julie?
Yes.
Okay, great. Great. What is this thing on your back?
This?
Yeah, Miffy.
It's like a bunny.